go ahead and get started. I'm actually thrilled with the size here. A, because I wasn't exactly sure anybody would show up. Secondly, the size being what it is, we can be a lot less formal than would be if it was bigger, which is good. Before we get started too official, we have to obviously recognize our sponsors. Without them, the conference wouldn't be here. We thank them for the food that's
yes.
Food.
They're sorting food now.
Visit them, Dev Express. They're good. I've actually just started using Dev Express. CodeRush. Good stuff.
CodeRush and Refactor Pro, they go together.
Just started using it. It's great. So this is going to be a. How many people have been in talks like this before? A couple people. So I work, for those who don't, a real quick introduction, I work at Oak Ridge National Laboratory. I'm a computer science research group. If you don't know anything about Oak Ridge, we do lots of big compute. We're the home of the 2nd, 8th, 30th, and 32nd fastest supercomputers in the world. We're working on regaining title as #1 again because that's just what we do. China has it now. Like that. We do lots of that space. I am not in that group. So everyone else in my group does that. I don't. Everyone else is working on exascale things. They're working on how do you write code for something that runs at exascale. That's not the red-headed stepchild, focusing more on cloud computing aspects. However, as a hobby, because everyone else in my group is working on it, our next supercomputer, which was named Titan, will be a hybrid architecture, which will be AMD-based processors combined with NVIDIA cards on each node. And with that, we're hoping to hit the 20 to 25 petaflop range. Because everyone else is doing it, I've taken an interest in sort of learning, getting my feet wet. This talk will be sort of introductory and baseline, hopefully giving people an idea of what you can do and what some of the ideas and thinking and thought process, if you will, you need to go through if you're going to play in that space. So the real goal is just for you to walk away knowing more about CUDA than you did when you walked in. For some people, that might be easy because you didn't know anything about it before we talked about it out in the hall. For others, it may not be quite as much. We will talk a bit about why GPGPU, why do we care. I'll talk a little bit in that case why CUDA, and just sort of delve there a little bit. Talk about some of the applications where we can use it. It's not just for supercomputing use, so that's technical computing is the biggest space right now. Some of the toolings, and then we'll actually walk through a matrix multiplication example. The matrix multiplication example is going to be very easy. And if you've read any of the books that we're passing around, many of the examples, many of the slides come from those materials. And the reason is that the matrix multiplication example and some of the others help sort of introduce some of the primitives that we need to talk about. And specifically, please, I'll post the slides up on my blog when we're done. I would really appreciate some ratings, good or bad, because it's the first time giving this talk and I haven't scheduled a few more times. So if it's bad, I'd like to fix it for them.
Ratings are on your blog?
All of this stuff will be on the blog. So,
where do we submit the ratings? Sorry.
Right there.
Right there.
But this link will, if you don't remember that, the slides will be up on the blog, so you can. So by the end of probably tomorrow.
Where's this? I missed the first.
It's not there. It's on the last slide. It's my blog address. But it's my name, rob.gillenfamily.net. So it'll be on the last slide. So GPUs are designed for graphics. They're designed for pushing many, many millions of pixels very, very quickly. You don't know that. A couple of years ago, someone realized that, hey, we can start to sort of, much the way that scientific people are looking at the cloud and say, hey, we have this pool of computing resources that were really designed for horizontal scale web apps, but we can abuse it to do our technical computing. People looked at it with a similar eye at GPUs and said, there's this massive pool of processors that we can now sort of abuse to do math in interesting ways. This is a simple diagram of a traditional CPU versus a GPU, and you can see that ALU stands for arithmetic logic unit, so basically a math coprocessor, and you see that GPUs have a lot more of them. So if your dedication and your use of silicon is very different. Obviously, there are many types of compute that GPUs don't do well at, and one of the keys is to understanding where you do use them and where you don't use them. This is a similar architecture of an NVIDIA Fermi card. Just giving you an idea of how many cores. We talk about, a CPU having a dual core, quad core. I've got machines at the lab that have two 12-core chips in it, which is really great. The NVIDIA card has thousands of these cores, it's packed in there. So for doing massively multi-threaded apps, you're not going to hit on a CPU the level of hybrid nature or parallelization that you would otherwise. Yes?
So it looks like the cores are kind of grouped together and
Yes.
have some common infrastructure. What's that group called?
It's basically just the way they do. Some people call them blocks. It's basically just the structure of the thing. From a programmatic standpoint, we really think of it that way. Though there is some shared infrastructure that we'll talk about, some shared memory stuff. So if I have a block of computation that I want to interact with to share a piece of memory, we can optimize for that, and then sort of. There's an example of actually doing, if you will, a map reduce algorithm all on one board. So rather than having to distribute across multiple compute nodes, you can actually do it on one board with shared memory. So a number of threads working one piece that then reduces and steps down and so forth. Go ahead.
The blocks are assigned in, symmetric multiprocessors, like blocks of 32?
Yes, it's 30, it depends on the board, but I think it's 32 or 64, whatever. I think some of the smaller ones are 16.
Yeah.
To put it in context, one of these cards with single precision math is talking 1.5 teraflops of compute. Wow. So depending on what you're trying to do, what math you're trying to do, that's really impressive compared to what you can get out of a traditional CPU. One of the things I will mention as we pass these around, these are two great books. If you're going to read them, if you want to learn, I would read this one first. This one gives you a less theoretical, less technical view, but covers a broader span of the problems and tools available. This was written as a textbook for a collegiate class. This goes much deeper, but you can get into the weeds a little too fast here, if you will. So I would read this one first, and then this one gives you sort of the theory behind what you read. But this one doesn't cover quite as much of the breadth of the tools available on that GPU. This one covers some interesting things like shared memory, constant memory, zero copy memory access, and some things like that. Here's the magic chart. This is the Y GPUs, right? So we're doing floating precision. So this is a flop. The left chart here is the flops chart. So flops are floating point operations per second. So when we talk about Jaguar supercomputers being rated, that's such and such petaflops. That's floating point operations per second. Traditional CPUs, even this is as of 2009, fall of 2009. You're talking down here, low 100 some odd petaflops, or gigaflops. Sorry, I'm thinking for petaflops, gigaflops. But you can see your GPU is way up here. Now, interestingly enough, it's not shown on this chart because I took this chart from NVIDIA. The AMD rates for single precision are actually higher. Which they're in an arms race between the two, but the AMD rates for their Firestream cards are actually slightly higher than the NVIDIA cards are. The difference is, and one of the reasons why at the lab we're focusing on NVIDIA cards is their use of ECC memory. So AMD doesn't by default use ECC memory in their cards, which allows when you're pushing millions of pixels on a screen that are refreshing every 30 times a second, you don't care if one's wrong. When you're simulating a nuclear reactor, you do. So we'll take a slight perf hit for the accuracy gain. So we're sticking specifically with the NVIDIA cards.
I don't know how sensitive is the flops, in general? How sensitive is the gigaflops measurement to the particular board? So if you were to compare, say, this generation of NVIDIA chips with the last and the next, roughly what's the change between generations?
It's growing significantly. So in particular, NVIDIA's been doing this for a couple of years now. And if you look at their website, they've got a whole list of cards that are CUDA certified. And see, like, my MacBook Air, I almost did this presentation on it. You can actually do CUDA math on that. Right? It's not great, but you can. About a year ago, a little over a year, they actually released their Fermi cards. The Fermi cards are an order of magnitude different. The first cards where NVIDIA came out and said these are specifically for GPU computing. They're priced differently, so rather than being like a $400 or $500 high-end gaming card, they're $2,500 to $3,000.
Wow.
But if you're looking at a supercomputer, that's nothing,
much,
right?
yeah.
So they've come out with those, and that's sort of a monumental leap. So the cards, so I've got a 40-node cluster of these at work that have these I think it's the M2050, which is the card, and is roughly $2,300 to $2,400 a piece. Those are well into the teraflop range, 1.5 teraflop range for single precision math. And the expectation is that will continue to leapfrog. So I got those cards. So this lists the C1060s here. So the C1060s, so my M2050, it's the consumer versus the M versus C is consumer versus motherboard, or not motherboard, but server class. It's essentially the same board, just the M1s don't have built-in fans. They expect the chassis vendors to provide fans. It's really the only difference. So that they have a C2050 that's the consumer equivalent of mine. But the 2050s you can barely get now. They've got 2070s and 2090s out. The biggest difference there is the amount of RAM on the boards. So mine have, I forget what it is, it's like 3 gigs of RAM. The new ones have, the 2070s have 6 gigs of RAM. And then the other ones, I think the 2090s have 12.
Wow.
So depending on what type of problem you're working with.
And those cards are super awesome for sure. But for testing and development, if you guys want to do it yourself, I mean, gosh, you can get like an M, or you can get like a GeForce 240 or 270 for like $50 if you want to play with this yourself.
Yeah, exactly.
I mean, obviously the core count, you're only looking at like 98 cores versus 448, but you can buy it for $50.
Yes.
So,
and I went to Best Buy a while back for my machine at home, and I got
They're cheap.
I want to say I got a GTX like 470-ish, and I spent all of $200.
yeah, it's amazing what you can get.
And you can do, as far as the coding and the compiling, you can do everything. What you really care about is each card is rated with a compute level, so a true compute level, and what you really care about is that. So that has to do with what version of the language runtime, if you will, that it can support. So the lowest one you'll see is like 1.1, 1.2, 1.3, 2.0, so that's really what you want to care about. Particularly for personal dev tests, you don't need millions and millions, but you do want to care to look at that, depending on the type of stuff you're doing. And each of those levels is a complete superset of the previous, so if you see something with a compute level of 2.0, it does 2.0 plus everything before that. This is another sample of why this is a heat transfer problem, and in this test, they saw an 8.5 speed up using one of these cards compared to Fortran code running an 8-core, 2.5 gig Xeon processor. So that's a significant. And the cost differential is just amazing, right? You're talking about a $450, $500 card in this case that's easily killing a pretty powerful machine. Here's a G80, and a G80, so this slide actually I took from the guy who wrote this class, and the G80 was one of the cards they were using in their class, and this was an order of a couple of years ago worth of card. And this gives you sort of an idea. 367 gigaflops on one card. And at the time, that was 20 to 50 times with the current high-end processor. So again, this is a dated slide, but the point is you don't have to invest a lot of money, like you mentioned. You don't have to invest a lot of money to see some pretty interesting performance. These are equivalent slides for certain types of math. I have to specify that, for certain types of math. So this is the Tesla card that screams like crazy. This is an IBM Blue GP. We actually have both of these at the lab, and for floating point math, they're functionally equivalent.
Wow.
And in case you're wondering, this is cheaper.
How was the IBM?
Well, IBM continues to iterate, right? So they have, and just by looking at the case, you can't answer that question because they use the same style. But in this case, our IBM is about 3 or 4 years old. But What's also interesting, though, is the power consumption. This question came up earlier. These things do pull, especially at this size of the card, they pull a significant amount of power and put off a significant amount of heat. So you're talking, most of those cards require, if you're building a home box, if you go this level, you're talking about a minimum of 1,000 watt power supply required for your machine.
You're looking at like 220 watts for the card.
Yeah.
Being a double.
Yeah, you have to have multiple power plugs at home. Significant
power consumption on IBM?
I could tell you, but I don't. I mean, I can get the number. I can't tell you.
Is it 220 watts?
No, 470. You do everything 470.
Okay.
Because it sits on the same floor as Jaguar,
Mm-hmm.
and Jaguar's 7 megawatts. So you don't push 7 megawatts around it. 220. Just you bring it in at 13.8. Some of the applications. This is just sort of one of the things. Obviously, molecular dynamics simulation. This is one of the guys in my group does a lot of that. But there's also things video and audio coding manipulation, 3D visualization. These are things that are sort of more not in the completely nerdy scientific world that people still do. There's still some advantage to, if you will, your more ordinary, if you will, in their traditional. Here's the big key: single program, multiple data. This is the type of apps that generally the cards really excel at. You can bend some rules here and do some interesting things, but for the most part, single program, multiple data. What's interesting to me as a cloud guy is this is very much the same when we're looking at what type of scientific apps fit into the cloud. It's the same problem, right? It's the same type of thing. Obviously, the granularity, there's a number of scale questions there, but it's the same type of thing. Yes?
So the opposite would be multiple programs, single data?
The idea is...
Well, I know the idea on single program, but
right.
I'm not sure I have a good conception of the part that it's not good at.
Compute to communicate ratio is the easiest way to think about it, okay? So in a single program, multiple data, or a lot of times you're doing, I have one executable that's processing a chunk of data independent of all others, right? Now, I may do that one step, share a bunch of data and do another step. But my compute to communicate ratio needs to be significantly high. So I need to be doing a significant amount of compute relative to how much communication I'm doing between my individual instances of my processes, right? Whereas on the flip side, we were talking about Jaguar earlier, it really shines because it has this massively fast interconnect, custom interconnect. And what it's doing is the compute to communicate ratio there is really low. They do a very small compute step and then share data. Very small compute step and share data. In the cloud and in the GPU, you're going to get bit there because in the GPU, you don't really have interconnections between your individual processors, right? You write to memory, they all go do their work, and then you can collect and you basically move back and forth, right? So you don't have an inner network really between all of those. You can't step that way. There are some things you can do for cooperation between threads, but it's nothing like an InfiniBand or a custom crane network or anything like that. And the key thing here is your operation needs to be significant, right? There is you take a perf hit every time you move data between your CPU and your GPU, and that can sometimes be significant depending on how much data you're pushing. One of the things we found a number of times, it's more beneficial to actually redo compute on the GPU than actually pushing the data across, right, because of the efficiencies. So if we have a code library that needs access to, say, a large vector on the CPU, but we know we can regenerate that, we may pass the parameters to the CPU to generate it, to the GPU to generate it over there, then do some significant things and then pass just the results back, rather than pushing that full vector back and forth across that bus, because you can swamp that. The other thing to think is millions of operations, right? As traditional CPU programmers, we've always been taught, threads are great, but they're heavy, they're expensive, they're dangerous. It takes thousands of clock cycles to do up a new thread. On a GPU, it takes an order of 2 threads, or 2 clock cycles to spin a new thread. So they're really good at doing millions of lightweight threads, and that's really the key one of the key things to think about. So if you want to parallelize horizontally, it's very important. Another example of ray tracing. So this is a really common operation for GPUs. And what I want you to think, a lot of people miss how complex this is. You think about drawing this or thinking about doing the math to generate this, right? Obviously, laying the texture down in the back is basically a background image. Doing the 3D wireframe of the car is another step. But then you think, and look at this yellow line, right? Think about the math that has to be done to calculate the difference, the delta from there to here, with the light angles to actually calculate where that line has to be done. That's some significant math processing. That's one of the cases where GPUs are really shocking. Doing that on a CPU would take you a very long time. Here's some more ray tracing examples. Again, anytime you're thinking about shadows or depth perception is a really good example for ray tracing.
It's interesting to note, too, that like in your ray tracing, for example, that's actually a great example because that's where we're starting to see more integration of the GPU as a system resource and vendor applications like Photoshop, CS5, MATLAB, other things that are targeted. Like you mentioned your MacBook Air. Boy, that's great. You know, you slap CS5 on there and you can actually leverage that. And sometimes the user's not even aware of it, really.
Right. But another thing that's interesting, and one of the reasons why I'm interested sort of at a macro level of studying this, because one of the questions is, why the heck do I care about CUDA, right? And it's more about, there's sort of a school of thought that says, to be a good programmer, you really ought to learn a new language every year or every couple of years, because it simply helps, even if you're not using it in core skill set, because it helps you think differently. This is very much the same way. It's helping me think about programming in a different way. And I just flew in this morning, actually, from an event out in Microsoft this last week, Microsoft research event. And one of the head of the Microsoft research group out there was talking about where sort of vision casting, where he thinks the world's going. And he was talking about FPGAs and GPUs and hybrid architectures. And if you believe him, or if he's right, one of the things he thinks we'll see is an increased usage of dedicated silicon on a chip for purpose-built or purpose-targeted things. So you may have your CPU might have certain portion of it that's generalized for compute. You may have another portion of it that's generalized for, say, video decoding or video rendering. Another portion of it that's generalized for audio processing. Or you can take your things so you have essentially specialized blocks of compute on your CPU board. And it was all weaved into a larger conversation about where Moore's law is going and how that's affecting our multi-core count, and how people are going to effectively or not effectively utilize the processing chips that people are being given. And I think it's interesting, and will be interesting to see if that actually materializes over the next couple of years. That we see these highly specialized aspects or areas of the chips, and what that means from a programming standpoint. From a tooling standpoint, I am Microsoft biased, as you can probably guess. So these are all the Microsoft tool sets. You can do everything very well on Linux or Mac. I guess I was surprised as I dug into it how well the Microsoft stack is supported by NVIDIA. I expected it to be, I knew it was very well supported on Linux and so forth, but it is very well supported on the Windows stack, specifically even Visual Studio 2010 didn't come out with that stuff. Now, there is a caveat to this. If you're doing, so CUDA Runtime 4.0 just went gold like last week or the week before. Prior to that time, the version prior to that, the RC was out for a while. Before that, you had 3.2. 3.2 required, on the Microsoft platform, required the VC9 compiler, so that's equivalent to the Visual Studio 2008 stack. And even today, even with the 4.0 stack, if you want to compile for the 3.2 runtime, you have to have that compiler. They have made it easier with the 4.0 RTM. This wasn't so much so with the RC, but with the 4.0 RTM, if you're doing everything at the 2.0 or the 4.0 runtime level, you just need Visual Studio 2010. So it's a much easier install. The difference between Express and the full version, like Pro and Ultimate and all that stuff, Express will work for everything except for NVIDIA Parallel Insight. that only works on the Pro version and higher. NVIDIA, the Parallel Insight, I'll show you a screenshot of it in a minute, is a great tool. Up until when they first announced it a couple of years ago, it was actually, you could get it in the beta, but then they wanted to charge you through the nose for it. They've now made it free, which is great. It's a very, very impressive tool for that, for debugging. And all of these tools, with the exception of the Pro version of Visual Studio, all of these tools are free. So you can download them off. If you go to developer.nvidia.com, there's a CUDA zone, and you can download it all. It doesn't take very long to install it all. Here's parallel debugging. So they built in this is all within Visual Studio, so you can actually step through and debug code running on your graphics card, which is great. So you can set breakpoints and actually step through it, so you get high-level visibility. The same for profiling. So this is an artifact from the NVIDIA Insight tool, so I can actually see how I'm doing my streams, how I'm passing data back and forth, core usage both on the CPU going up to the thread on the GPU, so you get a significant amount of data and visualization and support for understanding how your code's actually performing and being able to profile it. With the 4.0 runtime, they now support templates directly in Visual Studio, so you can. There was a lot of magic's not the right word. A lot of legwork you had to do to get Visual Studio to sort of compile and build a project before the 4.0 tools came out. Now it's brain dead easy. And we'll look at why, but essentially it's a C. CUDA is a C language plus. So it's a set of I keep wanting to say C plus extensions, but that gets confusing. It's the C language with extensions added to it. And the way it works in Visual Studio, and it works similarly on other platforms as well, is it actually calls their compiler and VCC first, and basically takes that file, creates a device driver for their aspect of it, and then calls the underlying C compiler for the rest of it, and then marries the two together. So in this case, so it sort of hooks itself into the build pipeline. And you used to have to do that all yourself in Visual Studio. Now it sort of installs it automatically.
So the CUDA language itself is not standard C.
It's extensions to C.
But the standard extension is Pragmas or okay, we will see.
Yeah, I'll show you. It's. I'm not a C guy. I can figure it out, so it can't be that hard. So, this is just another picture showing you. This is the project that you get when you hit that new button. And it creates a CU file, which is just their CUDA file, so it's really simple. So we've talked about all of this good stuff. A couple of things we need to talk about before we dive much further. Host versus device, and this is just the terminology that they use. Your host is always your physical machine, so when they talk about code running on your host, that's code running on the CPU. So you'll see that used a lot. Device is whatever card you're talking about. So you'll see a lot of, and you'll see that prefixed as dev a lot of times. That's not dev as a developer, that's dev as a device. So the device driver, the card that you're running on. Some of the keyword extensions, and I'll give you context here, we'll look at some code. Global basically is a prefix for a method. Let me step out and show that. Before we get too far. Here's a sample. So these are prefixes to methods. Can you all see that well enough? Zoom in a little bit. So essentially you prefix various methods with that tag. So global means that that method is runnable on the GPU, but is reachable from host code. Okay, so it's runnable on the GPU, callable from host code, not callable from GPU code. So the device tag, which is another method that we saw back in the slide, if I put device there, that means it only runs on the device. And is only callable by code running on the device. You cannot call those methods from the host. Now, you can also prefix a method with host. So I could come here and put __host __. And that would mean that method's only runnable from the host. Now, they built in a shortcut that says it's effectively there. I don't have to go through and write that. So every method that's not otherwise decorated is automatically a host-only method. Yes?
So does this just speak to code visibility, like public, private, internal, or does this speak to just the architecture of the code you're writing, this can only be called from the host because
it's really code visibility and where it gets compiled and delivered to. Okay. Now, one of the things that is interesting is I can take a method and decorate it both with host and with device. So if I have a method that needs to be runnable both places, I can put both tags and it will get compiled both places. So I don't have to rewrite it or create a host-only version of the method. If the code is identical, I just tag it with both of those and it's callable both places. Let's look at a couple other things here. For the most part, this is standard C. So this is called a kernel. So anything that's decorated here is called a kernel. That's just what they call the methods that get compiled and delivered out to the GPU. I mean, they talk a lot about launching a kernel. That's launching essentially your job. That's job, the HPC term. But it's my batch of code that's the monster on the card. If you look at my main, this is just standard ANSI C with some decorations, right? So here I'm creating some arrays, creating some pointers. Here they're using, again, by definition, or by convention, they're using dev to say that I'm going to put this on the device. You don't have to put that there, it's just a naming convention. Then here you see, much the way you would call malloc in C, I'm calling CUDA malloc. That creates that space, or allocates that memory space on the card. That's one of the big things to remember is I want to say by default. It's not by default. The memory on the card is different from the memory, your system memory. There are some tricks you can do with shared memory, memory pinning, and things like that to access system memory from the card. But in general, you're actually allocating different spots. So this is basically saying on the GPU itself, I want to allocate a certain portion of its RAM for these arrays. Okay. Much like C, there is a corresponding at the bottom CUDA free. So just like I would call free on my code on my objects that I malloc in C to free up the memory, I would call CUDA malloc to free it up on the GPU. Otherwise, you leak memory. A couple other things to look at while we're here. CUDA memcopy. That's the method that we use for pushing memory either to or from the GPU, and it has different flags. This was a good example. CUDA memcopy host to device, device to host. It's somewhat self-explanatory, right? So, host to device, I'm taking whatever I've allocated or whatever memory block I'm referencing on the device and pushing, or on the host, I'm pushing the device. And the other, this is a really common pattern. I'm setting some stuff up, I'm prepping it, I'm pushing it to the device. Here I'm invoking the kernel, and we'll talk about that funny syntax in just a minute. I'm invoking the kernel, and once I'm done with my work there, I'm going to copy the results back and do something on the host to display it, and then it dies. Make sense? There's a couple of different things that you can do, device to device. There's some other different flags, but those are the two most common ways. You can also query your device. Let's see, one of these. Here's a real simple CUDA call. This is basically it goes out and reads and enumerates all of the CUDA-enabled devices on the system. This is my here on my laptop. So it's the GTX 460, CUDA, the compute capability is 2.1 we were talking about earlier. There are a lot of things that you want to do. You may want to look here. I gave a memory dedicated to it, or dedicated on the board. Things to be particularly interested is max threads per block is 1024. We'll talk about in a few minutes why that's important, but that's a number or a variable responsive to one. So as you're writing code, it's targeting maybe multiple GPUs or the unknown GPU, right? You're targeting code that's going to run something else. So you may need to query it for that information to optimize your algorithm use, your thread counts, and thread dimensions and so forth. Hop back over. Memory management movement, we were talking about that earlier. You have to be cognizant of, and we'll see in the next couple slides, GPU programming is sort of the antithesis of everything we've been doing in the managed world for the last number of years. The managed world, we've been talking about sort of raising the level of abstraction, letting people think more about the business problem they're trying to solve, less about how to do it. This is the complete opposite of that, right? You have to understand the card. You have to think about memory positions and how my memory is laid out in arrays and how I'm using my threads. The benefit, or the reward, if you will, is massive performance improvements for certain types of code, but that comes with the cost of having to get down to the weeds. In thread management, again, like we were mentioning earlier, think thousands or millions rather than 2 or 3. Right? You're doing massive parallelization. Blocks and threads. So a block, when I launch a kernel, one of the things I pass into it, when you see the triple chevron at the beginning and end there, I'm specifying how many blocks and how many threads per block I want to launch. And that basically is my unit of parallelization that I'm saying. And these books do a great job of digging in real deep into how all of that works and what my benefits are and or are not in doing that. That's one of the things that's interesting. If you read this book, they sort of gloss over some of the details, whereas this guy digs into that right away. And that's part of why I suggest reading this one first. When you call those parameters, you can specify a 3-dimensional array for both of those parameters. Or if you just specify a single value, it assumes a 1-dimensional array. So you can sort of start really easy and think, I want to have one block with one thread on it, right? Now, you're not getting a lot of parallelization there, but you can start that way, right? And then you can say, okay, I want multiple blocks, so I can say I pass in a different number for that first parameter and have maybe 10 blocks or whatever like that. But that's a level of parallelization. But I can then think of how many threads per block and get additional levels of parallelization. Yes?
So I don't know if I understand it correctly, but I have such a problem which is very well parallelizable.
Okay.
And with these blocks, one thread runs on one processing unit, right?
Yes.
And I can group together. I can say that the thread doesn't just compute one unit of computations, but I group together into blocks. That's what we do.
No, a block has multiple threads, and the reason blocks have access to certain shared pieces of memory. So the reason you care about blocks is I can say one block. Like, so if you remember my pointer, my diagnostic query my machine, the maximum number of threads per block was 1024. So I could actually, within one block that has access to dedicated, the sample we were talking about earlier is actually writing to global memory on the card, but each block also has shared memory that's visible only to threads on that block. So I can have
is that physical grouping of physical cores.
Right. So I can have 1,000 threads operating on that block interacting just with shared memory and not going to the global memory on the card. So for certain problems, I can see significant benefits there. Right. So I was hand waving and glossing over some things, trying not to be different. But the whole point with it says here 1D or 2D threads can be 1D, 2D, or 3D. That's really a convenience mechanism. Okay, so if you think about the types of problems that you may solve in a space, say a matrix, right? So a vector is a 1D thing, right? I have one long string of values, right? A matrix is generally a 2D set of things. I may have a 3D collection of numbers. The way I'm indexing into those, there's certain things that are more convenient for indexing. And that's when you care about this, right? If my thread, or my block can only have 1024 threads, I can make a 1D, I can instantiate a shape. So when you call it and you pass those dimensions, you're basically telling it this is the shape that I want you to instantiate yourself with. So I can say I want you to instantiate yourself with a 1D array of 1,024 threads. And I'm going to index that just with an X parameter, right? I could also say I want you to instantiate yourself with a shape of 256 by 256. And then I can index into that with an XY parameters as far as getting my thread IDs. We'll look at a little code that'll maybe clarify that. But the big point is the 1D, 2D, or 3D is really a convenience factor. It's not physically changing not physically changing the board.
And you're not forced to use it. You can do everything 1D and it's all good.
Exactly. It's simply a mechanism, a convenience factor for how you want to think about your problem and how you want to express your code in that problem. There are some codes, and this book actually is an example where they take a problem that they're doing some vector math, I think it's their matrix add problem set, where they do it initially as a 1D problem set, then they come back and do it as a 2D problem set, simply because it shortens the code, makes the code a little bit more readable and understandable, and that really clarifies that point. It's simply a convenience factor. It's not technically any different.
So it doesn't affect performance at all?
It's no, and they actually validate that. They set up timers on both sides, on both tests, and they show you that the time is exactly the same. It's not a perfect question. It's a logic question. How do I want to
totally use the next question?
Yes. This goes back to what we were talking about earlier. SPMDs. Block size 1 to 512 concurrent threads. This is old. That's actually now that's a factor of your card, so you want to query that and make that decision. Block shape 1D, 2D, or 3D. Thread numbers that you can index in. Nothing unique that we haven't talked about already there. One of the things we have to think about is the hardware is free to assign blocks to any processor at any time. So when you write your code, you need to keep that in mind, right? So you need to write stuff that is memory or is not dependent on other pieces, right? So I'm writing that block that's going to do one piece of work on one piece of data, period. It's not dependent on being close to another piece of data. Unless I do things with atomics, and there's some things that you can do with atomics and thread synchronizations overcome that. But by default, you have to remember I'm simply giving it my code, and it's going to spread it out however it wants to based on the scheduler on the board. Simple running example matrix multiplication. Let's step out here to some other code here real quick and see if there's something that we'll look at. This is one I want to look at real quick here. This is simply a vector add. So let's look at this. So here I'm creating three int arrays on my machine that will live on the host. I'm creating pointers to arrays that will live on the GPU. I'm allocating my memory. Here, all I'm doing is iterating for the size n. N is a pound defined that we've set to 100. That's just my length of my array, just a convenience factor here. But I'm just looping through and basically filling those arrays with random, well, it's not random numbers, but just numbers so we can play with it. I'm then copying those. So CUDA mem copies into the dev A pointer the value from the A array, allocates the space, copies it. Same for B, right? Nothing magic there. I'm now adding. Here's my triple chevrons, N1, passing in. That's calling my kernel function. We'll look at it in just a second. So here N says I'm running it on 100 blocks because that's what I defined N as, in one thread per block. I could just as easily say N divided by 2 and then 2 threads per block. I'm going to have the identical level of parallelization. Or I could say 1 block and 100 threads from that block, or N, I can flip it. It's all the same. For this type of problem set, right? There are optimizations in certain math problems where I may benefit, and that's why they give you that level of control. If I were using shared memory, where my threads were doing something specific on that block, I would care more. And this one I'm simply doing an addition function. And you see I'm copying it back down here, writing out the display, and then freeing it up. Let's come up and look at the vector add function. Very simple. So I'm adding, I'm taking in an int, and sending out an int. So I'm getting block IDX X. So this is one of the things I'm not going to dig too far in, but there are a number of fixed variables available to you in CUDA that allow you to index in. And this is sort of going back to what we said. You have block IDX, so basically your block index, your grid index, and your thread index. Those are fixed values that let you know where you are based on where the card has deployed you. So you can then, so in this case, I'm saying, from this guy, I'm wanting to get so block IDX is going to be, say, we said, what, 100 of them. So the first instance, this is going to be 0. So it's going to get the 0th element. Then another block of code, it may be 50. It's going to get the 50th element, etc. So it's going to get the nth element. So that individual piece is doing the nth item in that vector add array. Make sense? You also notice that there's not a for loop. I'm not looping through the array, or looping through the vector length, because I said I want you to parallelize this for the width of my array. So I'm going to have an n number of instances running all at the same time. Make sense?
Yeah, so the main code is running on the host. It sets up the arrays in shared memory, and then it sets up how you're going to use your computer on the GPU. It deploys this vector add
It invokes the
bit
kernel
of code out there, and then they just all go.
Yes.
Right. And then lower on, you're copying the results, the C array back.
Right, then let's say that's the release the hounds method.
Yeah.
So
The do it method.
yeah, we set it up and then we say go, and then we say okay, we're done.
And those arrays are not synchronized arrays, so they are regular C arrays. And because we don't have any dependence, we don't need synchronization, right?
I have
It comes back from
I have
the-
slot level independence
Mm.
because of how I'm writing my code. Which you're hitting an important point in distributed data programming. If all of these were indexing, say, slot 0 and C, I'd have collisions, right? But because I'm doing it all, each one's only handling the index for their particular block of code. I do have independence. So the arrays are shared, but I'm only operating. Each instance here, or each thread, is only operating on its particular slice of each of those 3 arrays. Does that make sense?
Yeah.
Now you can, and there's some samples in here that show you how to do it. Basically, do a sync thread. So if I'm doing operations where I'm doing a bunch of threads working together on a shared mutex, and then I need to sync them and then take a result from them, I can do that. But in this operation, I'm completely data independent, so I don't have to worry about that. Make sense?
No, the add method has the global prefix.
Excuse me?
The add method there has that global prefix, which
Yes.
means both. If it had
No. Well,
global
it means
host
it's
and
callable. It means it's callable from the host. It is not callable from the device code. Okay, so if I had another function here that was device only, it could not call global. Only a host code can call global.
But add could call it.
But add could call a device method.
Yes.
Okay.
Yes.
Oh, okay.
So that's sort of my, if you will, your interface in.
Yeah. So okay. So that's how. So
And you can have multiple global methods, right? But they run on the device, but they're only callable from host code.
And so when your host code finally calls that add method down with the triple chevron, that's kind of a synchronous call. That thread on the host kind of waits until all the results come back.
Yes. Yes, it is. Now, one of the things you may be wondering is why am I filling the arrays on the CPU? That's a good question. It's not a good perf story to do that in this particular case. The example is simply showing that you can copy them back and forth. I could, in this case, since I'm not doing anything else magic on the CPU, I could just easily have actually filled them on the GPU. Right? And from a perf standpoint, it actually would have been better because I'm not moving the data back and forth. Make sense? Example. Right.
And the device can only talk to the memory of the host. It's not like it can't go and read disk or anything like that.
The device technically can't talk to anything on the host. The device can talk to its memory. It cannot talk to the host.
Oh, so the host is the one that transfers data from the host memory to the device memory.
The code that's moving data, shuttling data back and forth, is running on the host.
Right.
Right. Now, the caveat is that you can, for particular instances, you can basically pin memory. So I can do a zero memory copy operation where my code on my host can read into code to memory on the device. Or, excuse me, code on the device can read into memory on the host. But there's some magic you have to do because the pointers are actually different. So for the same memory spot, I'll have a host-specific pointer and a device-specific pointer, which will be different, but pointing to the same actual space. So you can do some interesting things there, but there's caveats there, right? Because as soon as I pin memory, you have all the disadvantages of pinning memory, which means it won't page it, so I'm actually eating up what's available on the host. There are cases when you really want to do it. There are cases when you can burn yourself. Make sense?
Yeah, so my point was you really have to stage up the data in memory that you're going to need to process on. You can't.
Yes, your GPU cannot read your disk.
Yeah.
They can't read across the network. They can't say, hey, I want to pull something from a web service.
Yeah.
That's CPU code. GPUs think vector math, or floating point math. You're getting math calculations. Let's see if there's anything interesting in this one. Yeah, so this one's sort of interesting. So this is a reduce, basically does an in-place reduce. And here you see it's got sync threads function. So that basically says, I know that this block is going to be running on all of them, and you all can go do this stuff, but at this point I want everybody to sync up and say, okay, we're all at least at this spot before proceeding forward.
That's a built-in method?
Yes. Yes, there's a number of built-in functions. So there's sync threads, if there's like a sync blocks or something. There's a couple of different primitives we can say basically synchronize it, make sure we're all caught up, and then continue on. Now, one of the things that's important to remember is we said it's SPMD, it's not SIMD. So it's not single instruction. So you don't have all of your codes not operating the same instruction. While they may be doing the same instruction sets, they're not doing every instruction lockstep. But this is a way for you to sort of sync up and say, okay, we need to make sure everyone's here before we're done. Now, the other thing that's important to note here is this shared variable, or the shared vector. So that's saying I have data that's in that shared memory that's only available to threads within my block. Right? And that's why I want to sync, because I'm interacting with that, and I want to sync threads within my block, and I'm going to go process that and sort of do a reduction. So, and the point I'm trying to get across is there's a number of primitives you can use for different different problem sets, right? If there's anything else interesting. You will see down here that when we invoke it, we're doing. Well, here we have this really handy, well-named variables that tell you exactly what we're doing. So, blocks per grid, threads per block, right? And the grid is the entire space that I'm allocating for my kernel launch. So that grid can have one or more blocks. Each block can have one or more threads.
But all on a single physical chip or card. Okay.
Yes.
So it would be much different code if I wanted to use two of the GPUs.
Two GPUs generally requires two CPU threads.
Okay.
So you can do it, but you need to be thinking multi-threaded CPU code. Now, that's caveated by CUDA Runtime 4, lets you do some GPU to GPU communication over SLI. So if you have identical cards and you're using SLI, you can do some really interesting things between the two of them without ever coming back to the CPU. So if you can imagine, and the meeting with the vendor last week, so Dell will sell you a box with eight of these NVIDIA cards. I can actually pass work to them and have them all communicate back and forth to each other over the PCI bus that I record to the CPU. Now, there's a lot of thinking you have to do that. You have to have a very complex problem to warrant that. But that's a 4.0 construct. But you can do, obviously you can do multi-CPUs. Another thing I should say, if you want to kick this stuff around, for $2.10 an hour, you can have a box in Amazon Web Services that has two of these cards in there, and two of the big fat ones.
Okay.
The M2052. So you can have almost 3 teraflops of compute for $250 an hour, or $210 an hour. And there's actually a German hacker who demonstrated cracking SHA-1 in like 45 minutes on one of those instances. Very interesting.
Is the WPA tool there?
Yeah.
GPGPU, correct.
Yeah.
Yeah, it wasn't anything new. It was simply showing how you can use that computer to do something
Interesting.
Yes.
Yeah, look too.
Okay, back here. We have a few minutes left, so we'll kind of move through this. We've covered a lot of these things. Everyone remember their matrix multiplication steps? Good. How was their design? So really simple. 2 blocks, I'm going to multiply, end up with a value in P. So P is my target. If we think about how memory is generally laid out in C, if this is my mental construct of the space, I'm laying it out in C as shared. So basically 2D to 1D memory transfer, visualization transfer. That will help you understand some of the code. Here's the traditional way of doing it on CPU. So what is the complexity of this? Yes. N cubed. Bad. Yeah, we don't like this.
Really bad. Really bad.
But there's frankly, while there are some optimizations, there's not really much more you can do on a CPU. Right? If you do this in C++, C#, whatever, this is where it's going to look like. Now, very simple. Taking my points. And the width offset here is just, if you remember from our memory representation of those spots, it's just jumping down my log array. We're going to walk through real quickly how we might do that on the GPU. So first thing we do is we set up this common variables. We're going to allocate space on the device. We're going to, for the 2 arrays, or actually for all 3. So here's M, N, and P. Then we're going to invoke the kernel. We'll come back and look at that more in detail in a second. Then we're going to copy it back, copy P back because we don't care about the others, and then we're going to free our memory. So conceptually pretty straightforward so far, right? So it's the same thing as we've been doing. We're allocate space, copy it up, invoke the kernel, copy the results back, and free our memory. Yes?
I think this is a side thing. But when you're allocating and freeing memory on the device,
Yes.
I mean, there are other things using the GPU at the time, like to print my monitor screen. So I'm sure that's also copying it over, doing something, getting it back. How well does what's the memory architecture?
So if you're serious about this, you will have a dedicated GPU for compute versus your monitor, right? And which you bring up an interesting point, because some of the visual debugging tools that I was showing earlier in Visual Studio will not work if I'm trying to display on the same card I'm trying to debug on.
So, in other words, when you copy memory over to the card, it does overwrite whatever it is, what's over there.
The CUDA runtime will make sure you're not screwing around with your display memory, right? But it's having to buffer that fight for you.
Mm-hmm.
So if you're, like I said, you can play around with this all day. But if you're really if you say you proved it out, and you really want to sort of do something perf-wise, you're going to be much better off having dedicated cards.
But to get started with it, it's not a concern. You're not going to screw up your display.
Exactly.
Yeah.
Because all the
algorithm.
You're not going to be dropping pixels or anything like that.
That's exactly right.
That's
That's exactly right. Because you got to think, when you're just using your display, you're using 1/1000 of the cores in the memory. Even with desktop effects and all the bling that we have on our desktops today, it's not even
Now,
scratching.
if you're playing full motion 3D video game,
yes,
while also trying to translate,
yes,
you might have some issues.
your frame rate might suck.
But you bring up a good point, though. The visual debugging tools in Visual Studio will not function. And they'll be nice about it. They'll simply say, I can't do this, right? Because essentially it's going to lock that card, right? And it can't display and lock all at the same time. Which is why I'm not stepping through and showing you visual debugging live, because I have one card.
You only have one copy.
Yes.
But you can use the profiler, though.
You can't use the profiler.
which is still great.
Yes.
So
Cool.
you maybe not use the whole device.
See, the profiler is not real time,
Yeah.
right? I mean, it calculates, it watches it real time, and then you analyze post.
Which is great. So even on your notebook, you can still use it.
Yes.
Cool.
Cool.
You just can't do the step debugging. Okay, now let's look at the kernel function. I've got it split up into 2 steps, and I've got a third slide that will show the whole thing together. So don't worry if if you feel fragmented. It is. So here's just the declaration, or sort of the declaration. I'm coming in, I'm passing in my arrays. I'm passing source array, result array, and width. Nothing magic there. And I'm initializing the value 0. And here, I wanted to have a picture here to sort of remind you as you're walking through the code, so I got it split up. Now, what's the big thing you notice is different here?
Only one big overhead.
Only 1 4 now.
Only 1 for loop. So I've lost two loop. So because I'm still doing the same amount of compute, but the card's doing all my parallelization for me. Right, so I didn't have to think about it all yet.
Is that because you picked a 2D choice for your threads? I guess what I'm asking is...
You'll see the implication here in a minute.
Right.
I'll show you the implication here in a minute. But I'm basically letting the card do all of my parallelization. I'm simply saying, for width, go do this.
And you got rid of the 2 for loops instead of the 3 for loops.
Yep.
Right.
Well, but you got rid of 2 instead of 3 just to keep the thread busy.
Yes.
That's what I'm asking. Okay.
So it's simply doing it's basically doing all of these values to get to here. So it's doing that pixel in the row and column 2 thread.
Right.
Where another thread is doing this pixel, and another thread is doing that pixel, etc. Make sense?
Yeah.
Super cool.
So here's the full function. So this is nothing different than what we were just saying. So it sets the resulting value object, right? So we invoke it. So I'm saying div grid, div block. And notice here I'm saying 1, and then I'm passing a 2-dimensional array with blocks.
What's the div 3?
So div 3 is a struct that allows you to do 3-dimensional. It's a 3-dimensional struct, right? And if I only set 2 values, it ignores the third. So that's technically what it takes. This accepts a div 3 struct value for both of these things. Though, as you saw earlier, we were simply passing a single integer. That's sort of the shortcut, easy way, which is what the CUDA by example book starts you with before they start getting you into the here's why we want to do multidimensional class, right?
Now there are multiple blocks on the grid, right?
There are. So you're sitting here thinking, we're only using 1.
Well, I'm also thinking you have a maximum of 1024 threads on your block. That's really easy to run out with.
Man, you think? You'd seen this before. We're only using 1 thread block. And yes, we're limited to the number of threads. So our array, if we allocated beyond our array size, like we get back here, into proof.
What's it? Does it blow up or does it not compile? You know, 1024, well, it would not compile.
It will compile. It'll just go down. It'll go south for runtime, right? So the question is, how do you solve the problem? 10 points?
You have to split it up according to the number of threads per block and parallelize it again, basically.
Subblocks.
Subblocks.
Right? So I basically take this and say, I want to block that, and have each block with its threads do a portion of the block and a portion of that. So again, and so now you say, well, I could go for as many blocks as my card has. Well, I think, actually, right now, the maximum number of blocks you can have is 64K. So I can go 64K blocks times my maximum number of threads per block. So that's 64K times 1024 in my case. So that's a lot of parallelization. But you can imagine I could still hit that, right? And so the solution to that is that if you want to fully do n number of, a non-predefined value of width, you would have to put a for loop around that to handle that case, right?
And do some sort of pages.
Yeah, essentially, it's paid,
Or you could, if you had more than one device, in the query examples, you could actually specify which device to use too. If you had more than one card.
Yes.
Which card? Okay.
Which card to use? If you had the luxury of having 2.
If you have multiple cards, and maybe you have one card that has more computational ability than the other, you could say, I want put this on that card, etc.
Can I put it to every?
I think you still need independent CPU threads to do that.
Because the call down to the device is a blocking call.
Yes.
The threads aren't hard to set up.
So you can do it. It's just CPU thread in C, which is slightly harder than the parallel for you. Yes. Yes. Thank you. Thank you. I got it. This is just a visualization that we're talking about. So I'm having one tile or one block do one little block. So basically doing those threads and another block at the end of the threads here, etc. etc. Simple visualization. Cleanup topics. So this is all of the stuff that we were going to talk about if I got to this spot and still had plenty of time. The key thing here is there are some. This is kind of interesting. There is a CUDA.net. So if you're a C# only guy and this stuff is sort of say that. There is a .NET wrapper. You can do some interesting things there. There's interesting conversations around OpenCL versus CUDA, pros, cons, etc. There. Microsoft has a product called Direct Compute, which comes out of the same team that does DirectX, but it's an abstraction across their basically allows you to do the same thing in their version of C. It's vendor card agnostic, so you're not tied to NVIDIA or whatever. But again, like with any abstraction, you're throwing away some of the fine-grained perf, right? So if you really, really care about perf, you'll pick one and stick with it. If you're a C# guy and just want better perf, one of those abstractions is still going to get you significant value. Atomics is an interesting topic we want to look at. We've talked about massive parallelization that sort of comes for free with your GPU card. That can also bite you if you actually need to do something once. And Atomics gives you the mechanism to do that, basically to say, I don't want anybody else to do this, I want one to do this, and then we can step back and keep doing the parallelization stuff. Thread synchronization, we talked about that for stage reductions. And at BCC, we talked about it a little bit.
Who uses OpenCL?
A lot of people, and there's in the research community, there's a lot of people who are talking about actually using OpenCL as a mechanism for sort of a generalized programming architecture across or programming mechanism across hyperarchitecture.
I think it can do this multi-GPU better.
It can, but again, you're throwing away. It's an abstraction, right?
So it's like the device compute thing from Microsoft.
It's like the direct compute, right? It's a layer up that abstracts the specifics of your ATI card or your GP or your NVIDIA card, etc. But you get a little more magic for it, right? To take my cloud example, it's the Azure versus Amazon. I've got full control in one, but I also have full responsibility. I get a little more magic over here, but I'm also losing a little bit. So depending on where you want to play, depending on whether or not it's right for you.
Another route to take between having to choose between OpenCL versus CUDA is you can actually use some tools that are under development right now, like the CUDA tools for dynamic code translation. So you write your stuff in C and actually have it actually translate it into the CUDA code. And the performance on that looks pretty impressive. I mean, it's not as good as hand coding it all in CUDA, but you're getting about 80% of the bang for your buck.
That's pretty good.
Which is not bad.
And we've got a bunch of similar efforts at the lab because, as you can imagine, if we're moving from a traditional CPU architecture for our scientific codes to this hybrid architecture, one of our big problems is how do we re-architect codes to actually leverage that platform?
Yeah.
There's a number of things, and trying to do that automatic is interesting but challenging, and there's...
And it's a moving target right now, so it's really hard.
Yes. Oh, and the big, cool, interesting thing is this morning, Information Week posted that Microsoft has an acquisition plan with NVIDIA.
Not with Nokia?
No, with NVIDIA.
I might tweet both and see what happens. Interesting.
You had a question?
Well, so we're doing a lot with the parallelization with Link, right? So that
Yes.
people can leverage the cores in the machines,
Yes.
the CPU cores. Is there a provider for CUDA for that? You know, I would think that'd be easily portable by the framework team to use
I
the
believe
GPU.
that's part of what's built into direct compute.
Okay.
Is a mechanism that's tied to that. There's not, as far as I know, there's not a...
Because I could write the same query and do for a GPU or something on the end as an extension.
Yes.
And we're just going to the GPU.
So as an instructor, I would say leave that as an exercise for students.
I was going to mention one other thing. If you want to get started, the books are really, really good for sure. There's another great resource. I forget the fellow's name, but he's with Lawrence Livermore National Laboratory. He's got a series of articles on like an introduction to CUDA. It's like a 10 or a 12-part series, something like that.
Yeah.
It's a great resource, and it's online. You can just start.
If you go to the developer zone, so developer.nvidia.com, go to the CUDA zone, they've got this whole space is probably the most open as far as learning that I've seen. They've got the guy who did this course. You can actually, it's linked to on that site. They taught at the University of Illinois. They actually have videos for every single course.
Wow.
They have the homework assignments. They have the solution things.
Wow.
And he's not the only one. There's like 4 or 5 other universities that are also linked there. So you can actually sit and take the entire course, and it's all free. It's great. They've got there's all kinds of resources there so you can sort of study yourself into the ground very quickly. And it's great. Yes.
So this whole thing evolved from the shaders.
Yes.
And I remember the early days. These shaders had limitations how many lines your shader code can be, how many variables can you use. So what are the current limitations today? Can I run into limitations that my code, what I want to run on the processing element is too big? Or
So that class that I just told you about, this guy's class, is lecture number 1 or 2. He actually talks about that exact thing, explains what they've done at NVIDIA to eliminate the shader limitations.
That's part of the CUDA architecture. Is NVIDIA got wise to this a while back and realized that their forward roadmap in CUDA was to address some of those concerns and come up with the unified device architecture to overcome some of those limits. It's built in by design, kind of.
And he explains so this one of the guys. This is 2 people teaching this class. One guy's at the University of Illinois. One guy's from NVIDIA. And they co-taught it, so you get a lot of hands-on industry discussion. Just a second. Blog and please rate. Again, I'll post this up there, but if the talk stunk, let me know. If it was great, let me know. You lied. But it'd be great to know because I'm planning on getting this talk from Yes?
even a very complex code can run pretty quickly.
Yes.
And is there a need, what do you think, if it takes very little time to compute one basic computation unit, to group them together into good jobs? Or because the thread is so cheap, you said 2 cycles, that I just let them run? Or you have this matrix addition example?
The big key is thinking through how expensive it is to move stuff onto and off of the GPU. And that's why you'll want to do testing. If your problem set's not sufficiently large, so if I do my matrix multiplication thing with, say, a width of 256, it's not going to be more sufficient for me to move that over to the GPU. If I'm doing it with 10,000, it probably is. Right. So you have to do some testing based on your problem size.
It's the compute to I/O. The more compute, the bigger bang.
Yes. It's like any optimization. Simply doing it because you can doesn't mean you should.
Yep.
Thanks, guys.
Cool.
Thank you.